All right, take a good look at this chip. This right here? This is the ancestor of pretty much every computer processor out there today, the legendary Intel 8086. And it pioneered two brilliant ideas that are still totally essential. First, how does a computer deal with something totally unexpected, an interruption? And second, how does one little processor learn to stop flying solo and start leading a whole team of specialists? Let's dive in and find out. We totally take it for granted, right? You're moving your mouse, you've got music playing, a file's downloading. It feels like a million things are happening at once. But here's the thing. A processor can really only do one thing at a time. So how on earth does it manage all that chaos? Well, the secret is all in a system for handling interruptions, a system the 8086 really helped invent. Okay, let's imagine the CPU is like this super diligent office worker, just laser focused on a single task, head down, getting it done. Then, all of a sudden, bam, the fire alarm goes off. Now, it can't just ignore it, right? But it also can't just drop everything and completely forget what it was doing. Our worker needs a plan, a procedure for handling that urgent interruption without losing its place. So, in the world of computing, that fire alarm has a name. It's called an interrupt. Let's start right there. In this first part, we're going to look at what these urgent pauses really are and where they even come from. So here's the official term, an interrupt. It's basically a special signal that pops up and tells the microprocessor, hey, stop what you're doing right now. You need to go run this special little program. We call it an interrupt service routine, and then you can come back. It's the official procedure for our fire alarm. So where do these things even come from? Well, they generally fall into three main buckets. You've got hardware interrupts, which come from the outside world, like a key press or a mouse click. Then there are software interrupts, which are signals deliberately written into the code by a programmer. And finally, you have internal interrupts. These are basically errors that the CPU causes itself, like that infamous divide by zero error. That one's so classic, it always triggers a very specific alarm. Interrupt 0. Okay, so an interrupt happens, the alarm is blaring, what's next? Well, the 8086 doesn't panic. Not at all. It has a playbook, a really precise set of instructions it follows every single time. Let's break that playbook down. Now, the heart of this entire playbook is something called the Interrupt Vector Table, or IVT. It's this special 1 kilobyte area right at the very, very beginning of the computer's memory. The best way to think of it, it's an address book. For every single possible interrupt, from number 0 all the way to 255, this table holds the exact address of the little routine that knows how to handle it. Yeah, this table really is just like an emergency contact list. If, say, interrupt number 2 gets triggered, the CPU knows to go to that exact spot in memory to find the instructions for that specific emergency. There's no searching, no guesswork. It is a direct, instant lookup. And this lookup triggers a super precise 4-step dance. So first, our office worker quickly jots down its current status, things like the results of its last calculation, which are called flags, onto a temporary notepad. We call this notepad the stack. Step 2, it basically puts a do not disturb sign on the door so no other interruptions can barge in. Third, it writes down exactly what line of the document it was on, also on that stack. Only then, with its place safely marked, does it jump over to the fire drill instruction. So this stack thing, it works just like a stack of plates, right? The last plate you put on top is the first one you take off. It's a last in, first out system. So by pushing its current status and location onto the top of the stack, the CPU is basically leaving itself a perfect bookmark. It knows exactly where it left off, so I can come back to the exact same spot later. And when the job is done, when that interrupt service routine is finished, a single command, IRET, which stands for interrupt return, reverses the entire process. It pops the saved address and flags right off the top of the stack and loads them back into its internal memory. In an instant, the CPU is right back where it was, as if nothing ever happened. Pretty slick. But what happens when the fire alarm, the phone, and the doorbell all go off at the exact same time? The system needs a way to prioritize, right? It needs to know what's most important. Well, first off, not all hardware interrupts are created equal. Most of them are what we call maskable, which just means the software can choose to ignore them for a little while. Think of it like putting your phone on silent. You'll get to the notifications later. But then there's the non-maskable interrupt, or NMI. This one cannot be ignored. It's for absolute drop-everything emergencies, like if the power is about to fail. And if a bunch of different interrupts happen at the exact same moment, there's a really clear hierarchy. An internal CPU error or software interrupt, that takes top priority. That emergency NMI we just talked about is next in line. Then come the regular hardware requests from your mouse or your keyboard. The point is, the CPU always knows exactly which crisis to handle first. Okay, so the 8086 is a master of juggling tasks. It's great at multitasking, but some jobs are just too specialized for it to handle on its own. And this is where the 8086 evolves, from just being a solo worker into a full-blown project manager.
See, the 8086 is a generalist. It's really good at a lot of things, but it's not a math genius. So what happens when a program needs to do some really complex, heavy-duty floating point calculations? The 8086 needs to call for help. It needs to bring in a specialist.
And the solution is just ingenious. It's built right into the hardware by just flipping a single switch on the chip, literally just connecting one specific pin called MN/MX to ground. You fundamentally change the processor's entire personality. It enters what's called maximum mode. And in this mode, it stops trying to do everything by itself and gets ready to lead a team of other chips. So let's actually build one of these teams. We're going to see how the 8086, in maximum mode, assembles a whole group of helper chips to create a system that's way, way more powerful.
Okay, so the very first thing the 8086 manager does is delegate. Instead of trying to manage all the system's communication lines, what we call the bus, by itself, it sends out status signals to a dedicated chip, the 8288 bus controller. This chip becomes the traffic cop for the whole system, generating all the necessary control signals to keep things flowing. Next up, you add some helper chips called latches. See, the 8086 uses the same set of wires to both shout out a memory address and to later send data. To keep things from getting confused, these latches act like a temporary post-it note. They latch onto the address the moment it's sent out, holding it steady so those main wires are free a split second later for the actual data to go through. It just keeps all the communication super orderly.
And here's where the magic really happens. Specialized chips, like the amazing 887 math coprocessor, can now use these special request/grant lines to literally ask the 8086 for permission to use the system bus. The 8086, acting as the manager, gets the request and says, "Yep, go ahead." It grants access. This allows that specialist chip to take over, do its super high-speed calculations, and then hand control right back. And when you put it all together, you get this, a complete multiprocessor system. You've got the 8086 as the orchestrator, the clock setting the tempo, the bus controller managing all the traffic, and these specialized coprocessors on standby, ready to jump in. It's not a single chip working alone anymore. It's a high-performance computing team. You know, this whole idea, which seems so obvious and fundamental to us today, was pioneered right here. When your computer's main CPU works with a GPU for graphics, or a chip for networking, or another one for sound, that is a direct evolution of the team-based system that was created for the 8086's maximum mode. It all started here. So, from gracefully handling interruptions to orchestrating a whole team of specialists, the 8086 really did set the stage for modern computing. And it kind of leaves us with a pretty fascinating question, doesn't it? If this was the beginning of teamwork between chips, what does the next evolution of that collaboration even look like?